Okay, so we're going to try this, and this is going to be our first attempt at this. Um, in this unit, I want to try having you do your homework by getting your notes taken care of, and then in class we'll actually work together with the information. So basically the stuff that you would normally have been doing at home by yourself, you'll be able to do in the classroom with other people. So here goes. In this first lecture, this is our first one in Unit 2, Electrochem, and in this first lecture you're going to learn about electrochemical cells and reduction potentials. I need you to make sure that before you start, you actually set up your foundation of learning by doing the learning targets that are on the next slide. So make sure that you have your learning target notebook and find your textbook, and you're going to skim the reading and make your start of your notes, your introduction from your reading, and set it up in your learning targets. Please make sure that you leave space as you watch through the rest of the video. Okay, so I'm going to show this slide, and you're going to want to pause the video here and go ahead and get this small introduction in your learning target notebook. Make sure that you leave space, especially for examples and things that we're going to add together as I continue through the video. So right now, pause the video and do your learning targets. And then you can stop the pause or restart the video and learn what I want to have you learn from me. Okay, now that you have an introduction, you have restarted the video, so let's go ahead and get started. We're going to use the information that you learned in our information about redox reactions to talk about electrochemistry. And there are two types of electrochemical cells. These would be voltaic cells, and also called galvanic cells, and electrolytic cells. You should have already learned this from your reading, but electrochemical cells basically either are redox reactions that create electrons or create moving electrons, and those would be our voltaic cells or our galvanic cells, or they're redox reactions that are forced by electricity, which is an outside source of electrons causing the reaction to happen, and those are called electrolytic cells. So they have some commonalities, and they have some things that are different that you need to try to keep straight. And so we're going to run down through these really quickly, and most of this should be information that you already have in your targets, but please make sure that you pause the video and add as you need to. I want to talk about one thing at a time here in the comparison so that you can kind of get an idea. The voltaic cells are something that we call spontaneous. This is an old term compared to thermodynamics, and we haven't done that yet, but that's okay. It basically means that the reaction will occur on its own without constant force a force of something creating that reaction. So the new terminology for that would be product favored. In other words, the reaction just goes ahead and creates products on its own. So you can use either spontaneous or product favored, but voltaic cells, the reactions just occur on their own. In electrolytic cells, they're not spontaneous, so we call them reactant favored. This means that there has to be a source of electrons for this reaction to occur. So that's one thing that's different about them. Related to that would be what we call the standard cell potential, and you'll learn more about that in what we keep doing, but you should know a little bit already from your targets. And this would be that the value of the standard cell potential for voltaic cells is positive or greater than 1, and the standard cell potential for electrolytic cells is negative or less than 1. So if you solve a reaction for the standard cell potential, you can tell whether or not that reaction would occur be product favored, or whether that reaction would be reactant favored based on the sign on the value of the standard cell potential. The next thing you want to think about is that electrons in voltaic cells move automatically, that it's producing electron movement by the reaction occurring spontaneously. So it's basically what we have in our batteries. When we're using our batteries, we are completing the circuit that's created, and the battery cell is creating the movement of electrons, and we're just harnessing it to run whatever we're running out of our battery. Electrolytic cells, however, require a source of electrons. So something has to be plugged into a battery, or something has to be plugged into an electrical circuit like the outlet in the wall, and then the electricity causes the reaction to occur. So big difference. Voltaic cells produce this reaction, and electricity is produced, and and electrolytic cells, electricity is causing the reaction. So the electrons are basically pushed in electrolytic cells or attracted in voltaic cells. Something that's really important is that when we talk about this, if you have two containers, then you're talking about a voltaic cell. But if you have one container, then often you're talking about an electrolytic cell. We can have those spontaneous reactions of voltaic cells occurring in one container, but it's not going to harness the electricity. The electrons will just be a direct transfer, and this is what you would normally have called a single replacement reaction. So picture when you put the aluminum wire down into your copper 2 chloride in our lab, there was a direct electron transfer. It was a spontaneous reaction, but it was in one container, so we weren't able to harness the transfer of electrons. So the biggest deal here is that in voltaic cells, we want to be able to utilize the electrons that are being transferred for some other purpose. So they're usually in two separate containers so that the electrons have to travel through the wire. Okay. Something else related to all of this is that they both have something that we call a cathode and an anode, and so these are collectively called electrodes. Okay, and the electrodes are literally the source or the place where electron transfer or conductivity occurs. Okay, so this is just something that's allowing the electricity to be conducted into our solutions or out of our solutions. And so they both have a cathode and an anode, and in both cases, the reduction reaction occurs at the cathode and the oxidation reaction occurs at the anode. So this is that saying again, red cat or an ox. I talked about that when we first started oxidation reduction reactions. They both also require the electrolytic solution that has the ions involved in the solution. So if you're worried about iron in your reaction, you need to have iron ions in solution. Or if you're worried about calcium in reaction, you have to worry about calcium ions in solution. Or chlorine and chloride ions. So this is something that you have to be really careful of. Something that's different about those electrodes is that in the voltaic cell, the cathode is positive, and that means that the electrons are being attracted to it so that the reduction can occur. And it's positive relatively speaking. Relatively speaking, the anode is negative because there are extra electrons there and it's repelling the electrons away from the anode. So the electrons will always move from the the cathode, from the anode to the cathode, always. It doesn't matter which cell you're worried about, but if it's a voltaic cell, they do it spontaneously, and then if it's an electrolytic cell, really what's happening is that the electrons are being pushed into the cathode, so that we say the cathode is negatively charged because it has the extra electrons pushed into it, and the electrons are pulled from the anode, so we say the anode is positively charged because the electrons are being pulled out of it, so it's missing electrons. Okay, so you definitely want to think about those differences in charges, and you have to remember that that it's a difference of, are the electrons being shoved in to the cathode and electrolytic cells, making it negative? Are the electrons being pulled out, making it positive at the anode? Or is it an attraction thing? So in the voltaic cell, where it happens spontaneously, the cathode is relatively positive, which attracts electrons to it, and the anode is relatively negative. You'll have to kind of figure out how to remember that. And one more thing, and when we do the cells in more specific detail, you'll learn this, but voltaic cells require something called a salt bridge, which stops charges from building up and allows the reaction to continue. Okay, so this is kind of the background of these. I also want to give you some background on standard reduction potentials. A reduction potential is the likelihood of that reactant to gain electrons. So we're basically saying that a more positive reduction potential will be more likely that the reduction would occur. Okay, so you have some charts, and these are determined determined in the lab experimentally. And so you have a few charts that tell you what's happening, and you can see that this is a sample of the one from your book. It's in Appendix D, or this is a sample, and I'll give you a paper copy of it, of the one from a few years ago on the AP exam, and they change it a little bit every year. It's also linked here, which you won't be able to click on in the video, but I will make sure that I link it or that I link this presentation so that you can see it and kind of go from there. So if you need a second copy, it will be linked for you. Something that you need to notice is that on these charts, these are always written as reduction reactions. Remember that these are called standard reduction potentials. So the reactions would all be written as reductions, as gaining electrons. So in every single one of these, the electrons are a reactant, okay? They're also a numerical comparison. It's some random numerical comparison, it feels like, is compared to the reduction of hydrogen ions forming hydrogen gas, and the standard there would be 0 volts. So if you're more likely to be reduced than hydrogen ions, then you would have a positive reduction potential, and if you're less likely to be reduced than hydrogen ions, you would have a negative reduction potential. Okay, so you're always looking at the more positive the value, and it doesn't have to be positive, but the closer to positive you are, if they're both negative, the more likely the reduction will occur. And you'll use this to decide in a situation which will be a reduction and which will be an oxidation. Some things that I asked you to put in your targets. This word standard is signified by this little degree sign on the E. So E is reduction potential, E standard has that little degree sign on there, and this means that your conditions have to be 25 degrees Celsius. If you have gases, the pressure has to be 1 atmosphere. If you have solutions, the concentration has to be 1 molar, and it's got to be initially when no current is flowing. So if you let a reaction occur, the potential will slowly become less and less. So this has to be at the very beginning. So you have to think about that. And the standard System International unit of electrical potential is the volt. So we use capital V for the abbreviation. Something else that you need to know is that you reverse the half reactions to make them oxidations. So if you're looking at these reactions, you can say, I want to say that this is the reduction of lithium ions to lithium, but if I come this direction, now I have lithium forms lithium ions and an electron, all right, and it's now an oxidation reaction. So in order to make this an oxidation potential, we keep the same number, but change the sign. Okay, so this is something really important to think about because you'll do this a lot. All right, so if you reverse the half reaction, it becomes an oxidation and the sign becomes the opposite of the sign. All right, and to find the overall potential of a cell of 2 reactions combined, the actual redox, a reduction and an oxidation reaction, you can use one of 2 processes. I always use this, but most textbooks, and your textbook included, don't teach it that way. I like to pick the reduction, change the other one to an oxidation by rewriting the reaction and changing the potential to something called an oxidation potential, like I showed you here. Okay, so this right here would be an example of how to write it as an oxidation and determine the oxidation potential. Your textbook teaches it as the reduction potential and then add them together, sorry. So the reduction potential plus the oxidation potential gives you the overall cell potential. Your textbook teaches it as the reduction potential at the cathode, which is a reduction reaction, right? And the reduction potential off the chart of the oxidation reaction, which really is not what's written on the chart, but you're going to read it off the chart at the anode, and then you subtract it. So notice that you're doing the same math. Basically what I'm doing, or basically what you would be doing here, would be I don't know, it's just the same math. I'm changing the sign and adding, they're subtracting. So pick your method. I will always do it, E reduction plus E oxidation. And I find that easier. If you like it better the other way, then you can do it the other way, but don't mix and mingle the 2 or you'll be really confused, okay? And something that's really important is that we do not multiply the potentials of half reactions by stoichiometric coefficients when we combine them to give us our cell potential. Okay, so this is the only time I think in your life that you won't worry about those coefficients, but we don't do that. So I'm going to do a couple of really quick examples so that you can see them. You can add them to your targets, and we'll kind of go from there. All right, so the first thing I want to do is use the reduction potential chart to calculate the standard cell potential for the following reaction. So I need to identify what's happening here, and I see that I have Fe3 plus forming Fe2+. And I can start to worry about where the electrons are and all of that, how many of them, or I can look it up on the chart. I can also see that my other half reaction is Cu forms Cu2+. So this is the reduction, and this is an oxidation, which means that I'm going to look at the chart, and I'm going to look for Fe3+ on the left on the chart, because the chart is written as reductions. So when I do that, I'm going to come up here, and I hopefully included it. I'm going to use the College Board one. So I can come up here, and I can find Fe3+ forms Fe2+. I can see that I need to add one electron, and that the potential for that is positive 0.77 volts. So I'm going to say we're going to add one electron here, and the E of reduction is positive 0.77 volts. Now I'm going to do the same thing for the copper half reaction, but this is an oxidation. So I need to look for Cu2+ on the left, because I have to reverse this reaction to find it on the chart, and Cu solid on the right. Okay, so when I do that, I come back up here, and I can see it right here. Okay, so I can see that the way it's written as a reduction, the reduction potential is 0.34. This means when I reverse the reaction, like I have below, it's going to be an oxidation potential of negative 0.34. Okay, so I'm going to come in here and say my E of oxidation is, oops, let me move it. My E of, I have, plus 2 electrons here. And my E of oxidation is negative 0.34 volts. Okay, so the way that I'm going to do this is E reduction plus E of oxidation equals the standard reduction potential for the cell. Okay, so I'm going to say positive 0.77 plus negative 0.34 volts, include your units, is positive 0.43 volts, which is the standard potential for the cell. Okay, and I didn't ask you to balance the equation, but notice that right now it's not balanced. So if I wanted to balance the equation, I could come back in and do it, but I don't have to be able to figure out what we just did. I would have to notice that this is 1 electron and 2 electrons, so I'd have to come back in and multiply this one by 2, and then add them together. So if I wanted to balance it, I would end up with 2 iron 3 and 1 copper. I can leave the 1 off, obviously. Forms 2 iron 2 and a Cu2+. And so we can check it the same way we checked them before, by substance and charge, and you'll see 6 positive on the left and 6 positive on the right. Okay, so this is how you use your reduction potential chart to figure out the standard cell potential. I want to do one more reaction with you quickly, and this would be that I want to have to make the decision now of which will be the reduction, which will be the oxidation. I want to put them together and calculate the standard cell potential. So I need to come back and look at my chart and notice that these are both written as reductions, so they can't both reduce. But I'm going to look up the E of reduction for each of these. So when I come to my chart, I'm looking for aluminum ions forming solid aluminum. Those are right here. And barium ions forming solid barium. Those are right here. And so aluminum's reduction potential is negative 1.66, and barium's is negative 2.90. So I'm going to go add those to what I have down here. Negative 1.66 volts, negative 2.90 volts. And now I have to make a decision. The one that's more positive is more likely to be the reduction. So that would be the aluminum. That means that this will be the reduction, and this actually isn't going to occur like that, but will occur as my oxidation. So I'm going to rewrite it. Ba forms Ba2+ plus 2 electrons. And I'm going to, let me move this over quick, and I'm going to then write the oxidation potential as the reverse sign of this, so positive 2.90 volts. And now I have 2 halves of a reaction. Okay, so for the standard cell potential, I literally can come in and add these two together. And when I add negative 1.66 and positive 2.9, I get positive 1.24 volts. Notice that this is a positive value, so yes, this reaction will occur. It is what we call spontaneous or product favored, and that's what you have to have if it's going to be a voltaic cell, is a positive overall potential. Okay, and now I need to balance my equation. So I have 3 electrons in this one, so that would be times 2, and 2 electrons in this one, that would be times 3. And I can come down here and see that I'm going to have 2 Al3 plus 3 barium yields 2 Al plus 3 Ba2 plus. And so my overall balanced equation would be this. I can check it for substance and charge. And my E cell, my standard reduction potential, would be positive 1.24 volts. And so yes, this could be a voltaic cell. If you ever get the negative, that means you reversed the wrong one if you're trying to do a voltaic cell. If it's not a voltaic cell, it's okay that it be a negative value. That would be how many volts of electrons you'd have to put in to make the reaction occur. So we'll work with this some more in class. Hopefully this is a good foundation. If you need to review any of this video before class to fill back in things, please make sure that you do, and make sure that you bring those learning targets that have this completed with you to class so that you have them to use.